Great to see you here, so many people. Beautiful building. I'm really sort of envious of the facilities here that are really great for a conference like this. Only thing I ask is you don't read any news during the lecture. I know there will be another outrage coming from Washington, D.C., but let's wait until the break to find out. I visited here in Boulder some time ago, especially to meet my friend Andrzej Ehrenfeucht, who was a long-time professor in computer science. I first met him in Warsaw in 1959, if you can imagine that long ago. And he was here for many years. Alas, after retirement, he moved away to Arizona. But I was reminded that the computer science had just moved into their new building, and he was very pleased to have a big office. But he was the kind of person who never threw anything away. His desk would pile up higher and higher and higher, and then a piece of it would slough off on the floor, and he never paid any attention to that. One day he was working somewhat late, and when he went home, he forgot to turn the lights off in his office. And in the middle of the night, the security guard saw the lights and went to look in the office, and then he got this telephone call, Professor Ehrenfeucht, come quickly, your office has been ransacked. He loved to tell that story about himself. Now, how did I get here? I got here because of Facebook. A good friend of mine in computational linguistics is always posting on Facebook. I realized the other day Facebook has put postcards out of business because everybody says, oh, look at the spaghetti we ate last night and things like that. Anyway, a friend of hers had answered one of her posts and mentioned something about LambdaConf. And I said, Lambda conference? What could the Lambda conference be? So as there's you can find everything by looking on the internet. I found the link to the conference. I wrote John DeGoss and said, would you folks be interested in some talks on the lambda calculus? And one thing led to another, and so that's how I got here. But I hadn't heard of the conference before I saw it mentioned there on Facebook. Now, what I've done for setting up the talks is, and someplace these are posted in their website. Let me see, wait a second here. So I have a number of background papers there, some of my papers and some other papers there connected with the presentation today. So those will be available. And then also the notebooks from the presentations today will be available. So just wanted to mention that those things will be there. What happened to the other file? There we go. How many of you know something about lambda calculus? Oh geez, everybody. How many of you know something about combinators? So I may go a little quickly on some of this, and I wouldn't mind finishing a little bit early today anyway, so we'll see how it goes.
Well, if it's any help, I only got 5 pages in lambda calculus paper.
Okay. Don't hesitate to ask me a question. I can always stop to answer questions if you're puzzled or I'm not making any sense, so please. Now, I'm doing this first session in Mathematica, which is a rather weird thing to do, but a very good friend of mine, the son of the person who introduced me to Mathematica, Theo Gray, invented in the early days this idea of a notebook, and he had this really cool idea that you could have things that you could open and close so that you can go through your file. You can have a very long file, but you can easily see a sort of table of contents or something like that. That's one reason for doing this. I've made a lot of use of Mathematica. I don't necessarily recommend the programming language, even though Stephen Wolfram, who's a good friend, thinks it's an absolutely great programming language. But what they did is they combined functional programming, lots of numerics, symbolic computation. I made lots of use of algebra in Mathematica, and graphics. I can't draw good pictures on the blackboard, but when I gave the course in geometry, I could get really good pictures. Once you find the formulas for something, then it was really great to be able to see what they look like. So I've had a lot of good use out of Mathematica. But today, what I'm going to do is to use it for some just minor computation with combinators to give you a feeling that combinators are very simply defined and they lead to very long formulas. So we'll see how that goes. So here's the key question as I said it here. Is it possible to have this kind of functional calculus where functions and arguments are on the same level? And in fact, you can even apply a function to itself. And we'll see if that gets you anything. But then beside that, if it's possible, it doesn't mean that it has a good use. And so we'll see how that goes too. So here is some history. If you sit over there, I have to write on the board a couple of times. You might not be able to see the board, so just advise you that. So you can sit here in the front. Great. So there was a crazy Russian in Göttingen where Hilbert, the famous mathematician Hilbert, had his school. And so in the mid-20s, he came up with an idea of exploring a calculus where functions could be applied to anything, and he gave several rules and things for that. And people helped him write up his papers. He was a little bit odd person, apparently. And then he went back to Russia, and nobody heard from him again. They don't even know exactly the circumstances of his death. But in Göttingen, in Germany there, Haskell Curry, whom I knew very well, did his PhD there in the Hilbert School, and he discovered, after he had some ideas of his own, discovered the Schoenfinkel paper and then related to that. Now they came from different points of view. Schoenfinkel was really just thinking of some kind of mathematical functions that he could operate with in a very simple way. But Curry was interested in symbolic computation, really. How do you especially work out problems about substitution of one expression in another? And so he wanted to set up some general operators for performing substitutions. Curry was always a formalist. I don't think he believed in anything, any kind of semantics or any kind of Platonic truth of mathematics. He only did symbol manipulation, and he did it for years and years and years and years. You'll see how elaborate, if you look at his books, it was. But he took over that idea of combinators going on from the work of Schoenfinkel. Now, simultaneously, Alonzo Church had done his PhD in mathematics at Princeton under Oswald Veblen, famous geometer. Church wrote on the axiom of choice, and then he got a very good traveling fellowship for 2 years to Europe, and he went to Göttingen in particular. But by that time, he was thinking of trying to find a new foundation for mathematics to solve the Russell paradox. Frege's original idea, sets and classes, anything could be a member of anything at your own will, and then Russell realized if you're too free with that, you get to the Russell paradox. So Church thought for a long time that he had solved the problem with the Russell paradox by not using properties or sets, but using functions. And so he set up his lambda-calculus for defining functions by abstraction, by telling with combinations what the new function is supposed to be. And then he added onto that a number of logical axioms for proving things about existence of functions. And of course, early on it was realized that Curry's system and Church's system are equivalent. I'll show you a bit of the equivalence of that. Now, my good friend John Addison is the son-in-law of Alonzo Church. John was an undergraduate at Princeton, and then he went to Wisconsin where he did his PhD under Claney, who was one of the major students of Church and the founder of recursive function theory. And then he came back and married Church's daughter. He's been in Berkeley for a long time now. Once I said, John, why in the world did Church choose lambda for his operator? John said, oh, I don't know. I'll write to him and we'll ask him. So he wrote a postcard. Dear Professor Church, he always referred to his father-in-law as Professor Church. Dear Professor Church, Russell had the iota operator and Hilbert had the epsilon operator. Why in the world did you have lambda for your operator? Now, there are many stories about lambda. There's a false story that lambda is short for Lonzo, but that's not true either. But a very popular story is that Russell originally did class abstraction by using a circumflex over the variable, but printers had trouble with circumflexes on different variables. And so a printer said, I'll have to put the circumflex in front there. And then the circumflex changed into lambda. It's an entirely plausible story, but wrong. So Church didn't write a long letter back to his son-in-law. He just annotated the postcard and put it into an envelope. And where John had asked, why did you choose lambda? Church wrote very carefully in ink, as he always did, eeny, meeny, miny, mo. It's just another Greek letter. So that's the true story. Church was a very kind person, a great mentor to many students there, but he was a rather pedantic person, and my good friend who just passed away, Ray Smulyan, famous author of many puzzle books and things like that, was a student of Church's when I was a graduate student there. And he went to one of Church's lectures on elementary logic, and he remembers one day Church wrote a proof on the board, and then he turned to the class and said, now I could say we could prove the converse by interchanging the letters P and Q, but I'll do it again. And so we wrote out the whole proof again, very carefully on the backboard. Whenever he came into the room, he spent about 5 or 6 minutes erasing the board. We would always erase the board first, but he wanted a perfectly clean board. And that's part of his very careful approach to everything. That one picture there is about how he looked in the 1930s. And that was a very important time because the Institute for Advanced Study had just been set up. There was lots of worries about what was going on in Europe, and John von Neumann arranged for Griddle, who had finished his famous results in Vienna, to come to Princeton, and Griddle lectured on the incompleteness theorems there, and Church's two students, Kleene and Rosser, took very, very careful notes about that. In fact, learning what they learned from Griddle affected their whole academic lives after that. And so that was a very important thing that Griddle came to there. I knew Griddle pretty well. The one picture there is in his youth, and the other picture is the way I remember him. There are many stories about him. I'm just reminded of one story from Vienna. The Reitemeisters, who were old friends of Griddle from his graduate days, visited Princeton one year, and they decided that it would be very nice to take a drive in the country. And Griddle decided he would not go with them, and so Mrs. Griddle and the Reitemeisters went off in the car. And all of a sudden, Mrs. Griddle said, "Oh, it's so wonderful to be driving without a genius in the back seat." Mrs. Griddle was very outspoken. Now, in the 30s, you see, Griddle was there in Princeton a little over a year. Then he didn't feel very well and went back to Vienna. But from his lectures, which were very important with the question of what is a computable function and how to define things, you see, in the meantime, in Cambridge, Max Newman had been lecturing on logic and Griddle's work, and Turing was just, I guess, really just an undergraduate at that point when he heard Newman's lectures, and he set about trying to settle the question of the decision method. The decision method had already been formulated in the Hilbert Ackermann logic book about 1928, and so it was a big question. Is it possible somehow to mechanically decide whether a theorem in first-order logic is provable or not? And so that's how Turing started the problem there and invented his Turing machines. And so that was amazing result, and it was arranged that Turing could come to Princeton to do his PhD under Church. But when he got there, you see, this was the middle of the Depression, and Kleene and Rosser, Church's students, had already finished their PhDs, and they had to go to get jobs. And Griddle had long since gone back to Vienna, and so Turing never had a chance to meet Griddle, Kleene, or Rosser there. He had good relations with von Neumann, but von Neumann was much more interested in his work on numerics. Von Neumann was keen on computing and starting the ideas of mechanical computing machines. And we don't really have any correspondence or anything about what von Neumann thought about Turing machines and applications. Now, Kleene I knew very well. I couldn't find a youthful picture of him. He was a very lively person. He had most of his career in Madison, Wisconsin. Church had given him the project for his thesis of developing arithmetic in his Church's formal system. It hadn't been proved inconsistent. Yet, Kleene and Rosser, working together about the same time before they finished their theses, found the inconsistency in Church's system. But the lambda calculus was quite much developed by Church and Kleene and Rosser. And in discussions with Griddle, Church kept asking, well, is computability in the lambda calculus a sufficient definition of general computability? Church felt that the numerals should be represented by iterators. The number 3, for example, is the iterator that takes any function and takes f of f of f of f 3 times of x, iterate f 3 times. That Church said that represents the number 3, and so you can do lots of computations in pure lambda calculus with the iterators to do all kinds of numerical integer functions. And so Church kept asking Griddle if he thought that the lambda calculus was a good definition of computability, and Griddle didn't like it at all. Griddle and El Grande, the brilliant French logician who died tragically on a hiking accident, I think, they had had a lot of correspondence about computability, and they were generalizing the ideas of recursion equations. And so Griddle, Erbrand computability means you have generalized, sort of more complicated recursion equations, more complicated than primitive recursive functions there. And Griddle thought that his idea about recursion equations was better than Church's idea about lambda definability. However, Kleene was able to develop arithmetic in lambda calculus. The big block was how to define predecessor. And Kleene has a nice historical article. He writes, one day he had to go to the dentist, and while sitting in the dentist chair, he all of a sudden realized how to define predecessor. If we have time, I'll tell you later on what his trick was there. But Kleene was able to set the lambda calculus up so it could do all the kinds of recursions. And then, this is an important historical point. Before Turing came on the scene, and before Turing's work was known, Kleene had already proved that lambda definability and Gödel-Erbrand general recursion were equivalent, because he set up in lambda calculus how to do symbolic manipulation, how to take one formal system and mimic it in another formal system. And he gave a rigorous proof that Church and Gödel were equivalent before Turing ever came there. Then, when Turing arrived in Princeton, he read Kleine's paper. He never met Kleene, which is sad because Kleene and Rosser would have been most interested in his work. In a correspondence, Turing writes, after I published my paper on the decision problem, it just appeared the fall that he came to Princeton. He only had 2 requests for off-prints for his paper. Not many people took account of it. Of course, later, Kleene was extremely important for advertising Turing's work. But Kleene had already proved the equivalence of Church and Gödel, and as soon as Turing saw Kleine's paper, he could easily give a proof for the equivalence of Turing computability, and that too. I think Kleene should get much more credit for developments there. And one thing that he writes, after his thesis, which was all done in Church's lambda calculus, when he tried to lecture about it, he had a very hard time explaining it to people. They thought it was all kind of a weird system. So that's why he changed over to using just numeric functions. And of course, he used the Turing machine to do the universal partial recursive function. It was very important, too, that Kleene introduced partial functions. The earlier people always thought in terms of total functions. but it's better for setting up recursions and computability, and you know it. You have to use partial functions because you write a program and you say go, and you never know whether the program will stop or not. So you have to use partial functions to get a nice system. And so that's, in order to try to explain things, Kleene turned over to numeric functions and used the universal Turing machine, his notation. Curly brackets E of n means the eth Turing machine. When given the input n, then curly brackets E of n is the output of the eth Turing machine on input n. And of course, we've all the books about recursive functions follow along Kleine's original thing. So his co-student there, and that was very important for introducing Gödel's work into the States, his co-student was Barclay Rosser, and Barclay's thesis was on combinators, and it was the key question: can you do mathematics without variables? The reason why variables are annoying is that when you have free and bound variables, just think in terms of first-order logic, you have to be very careful when you substitute one formula and another not to capture a free variable by a quantifier in the sub part of the thing you're substituting into something. There are quantifiers here. You come with a free variable there. You shouldn't capture with your quantifier the free variables. It's very annoying to formulate exactly the ways to do that. And so the question is, can you do all of formalization of mathematics without any bound variables? Well, you can, but it's not very much fun to do. It does have a life now in two different forms. When the INRIA people did their implementation of the language ML, they wanted to have an abstract machine. You first translate a program into an abstract machine, and the abstract machine does things in very atomic steps, and then you can implement that abstract machine on many different platforms. So you compile to the abstract machine, and then you run the abstract machine on your favorite computer. And so they made very good use of combinators for setting up the abstract machine, and so that's a good use of them. Also, Dick de Bruijn from Holland introduced the idea of notating variables in such a way that you can automatically avoid any type of clash between free and bound variables, the de Bruijn indices. And so there's a big industry now of languages with using the de Bruijn idea. So the idea of logic without free variables is alive, but it's much more appreciated by machines than it is by people. So again, on the background here, I want to recommend that, what happened to it here? I thought I had it there. I want to recommend that there's a long paper. Oh, bless your heart. Why do you disappear on me here? There's a long paper by Roger Hindley here. And so, very long paper, lots of references there. So if you want more historical background about how things develop and how ideas related to each other, I strongly recommend Hindley's paper there, and so that's available. Okay. That is my historical introduction here. So I want to go on to the computations there. So why don't we pause here for a moment? Any questions? Anything? Yes, please.
Earlier on, you mentioned a question that Vega formulated, and then was sort of, then you said it sort of got a new incarnation in Russell's paradox. Could you go back and say just a little bit more about that?
Okay. So let's see. Russell liked to make some jokes about it and said there's this town where there are barbers, but some of the barbers need to have shaves, and so there is that barber who shaves all the barbers who don't shave themselves. Question, does he shave himself or not? That's Russell's paradox. In other words, it's the class of all classes that do not contain themselves. Is it a member of itself? If it is a member of itself, it's not a member of itself. Oops. That's Russell's paradox. And it really wasn't very obvious in Frege's original formulation. He formulated things in terms really of much more in terms of functions, and the question of the abstraction axiom, the class of all things having a certain property, wasn't as obvious in the way he formulated it. And so Russell, in thinking about how to use Frege's system there, realized that there was this if you're too free with things, then negation is a bad thing for you. And I don't have the exact way to describe what Claney and Rosser did for Church's system, but it's more in the line of the paradox of the least number that can't be defined in less than 20 words. Okay, think of the least number that can't be defined in less than 20 words. What is it? You have to be very careful with these things. One of my favorite think of questions is from the linguist George Lakoff, who writes a lot about political things. And the title of one of Lakoff's book is, "Don't Think of an Elephant." But I think of elephants every day, I'm afraid. Did that make sense to you? Yeah. So Church had thought that by using functions, it would be better than using classes, and it didn't work out. And so that was bad. Any other questions? Okay, let's see if I can get good old Mathematica to run here. So the way that Curry finally set it up, he only needed two combinators. The S combinator is named in honor of Schoenfinkel, and the K combinator is named in terms of constant. And it's a little more convenient if you also have the identity function as a combinator. Now, curiously enough, we are stuck with the ASCII keyboard, and Mathematica uses capital I as a special thing for algebra, and so I have to use the symbol J here in doing it. Some symbols are set aside for special uses, and some symbols are free for your own use. So alas, I have to use J for a moment for the identity function. And so also, Mathematica allows you to take function application as freely as you like there. Again, because we're stuck with the ASCII keyboard, round parentheses are saved for algebra, and so he has to use square brackets for function application. Mathematicians don't care. They shift between notations without any warning there, and you're supposed to understand what's there, but the computer has to have an exact thing there. So we use square brackets for function application. And so now the thing is that we can make rewrite rules in Mathematica. Mathematica is quite good at all kinds of symbolic manipulation. As I said, it's especially good at algebra. But you can make up your own rewrite rules. So the identity function is such that the identity function of anything x just disappears to x. It's identical to S, the Schoenfinkel combinator, means you take a combination of applications there. The way I think of it is x applied to y is application of a function to an argument, but you can parameterize applications. If the x's are parameterized by z and the y's are parameterized by z, then you can think of the whole suite of applications of one of the x's to one of the y's as a function of z there. So the Schoenfinkel combinator is parameterized application. And then the constant combinator, k of x is that function which constantly equals x no matter what argument y you choose there. So you said you were familiar with combinators there, so I take it everybody knows, everybody understand what the combinators are supposed to do? Question?
I always thought the S combinator as a distribution.
As the what? I can't hear.
I always thought the S combinator as a kind of distribution.
Well, it's a little bit like the distributive law in algebra of multiplication over addition there, okay?
Yeah.
And so you're thinking of an extra argument z which you distribute over the things there.
Yeah.
And that's symbolism and makes perfectly good sense because it tells you where to place your symbols. But I think if you think in terms of meaning of functions, my use of parameterization makes more sense. But there is nothing wrong in thinking of distribution. Any other questions? Please.
Just a question on the notation. What does the underscore mean?
Mathematica, in doing symbolic computation in Mathematica, there are many things that are already defined and many things that are taken as parameters. But again, because we're stuck with the ASCII keyboard, we don't have enough symbols there. So if you want to say, this has to be treated as a variable in a rule, you write that letter as an underscore, and then Mathematica knows that that's supposed to be a variable rather than something previously defined. You always get stuck with that. You try to develop a programming language, and you want to do more things than there are symbols for. Other question? Please.
Can I verify that I'm understanding S function properly?
Yeah.
So we're saying in this that for the so x is a function, y is a function, and z is a function, right?
Yeah, S is a master function that's going to combine functions into a new function.
Right. And so x is going to take as an input the function z. And
No.
No? Oh,
Just think of z as an input. We're not treating z as a function. Here, z is just some other input. But the input could be a function.
Okay, could be, but it could also be a number or a string.
And x itself can be something really weird, which says, oh, I better treat z as a function to do it. When I just write x of z, you don't yet know what x is going to do with z.
Oh, wait, so it might not be a function. It might be something else?
Well,
X?
everything is the same. This is a type-free system.
Right.
We make no distinction between numbers, functions, and other things there. So z is allowed as an input to x. And z is allowed to an input to y. And now I'm going to treat x of z, amazingly, as a function and apply it to y of z. Everything is allowed. You can apply anything to anything.
So wait, so we're applying x of z to y of z.
Of course.
But it's going from left to right.
So what? I can make any kind of combination I want. That's what combinators are supposed to do, combine things.
I'm just admiring the syntax.
It's very simple-minded.
I know. I'm simple-minded too, but I think I proved to be the simpler of the.
So even in Mathematica, we can make up these expressions here, but they don't necessarily compute right away. And the way we're going to do it is compute by means of rewrite rules. So when we see certain combinations, we give rules for reducing the combination from one thing to another. So the rule for S there is the rule for eliminating S. And we'll see how that works in some examples. Does that make more sense?
It's helping. I think I'm gonna let it sit, and then I might ask more questions in a bit.
I bet you will.
Me too.
Thank you, that was helpful.
Please.
Well, I'm not very familiar with lambda-calculus, but I have some knowledge of algebra. So basically, when I see like the combinator rule, so basically a combinator is just a function.
Yeah.
So I could take a function as input or a variable. All right.
Yeah. Yeah. And what it does is takes those inputs and recombines them. That's why it's called a combinator. Takes a whole bunch of inputs and recombines them into something else.
Which is actually what the function does.
And what's amazing is we can master all possible combinations by just using two, S and K, as I'll show you. You had a question.
Professor Scott, is the K combinator, is there a specific name that we use for that?
Constant. K stands for constant.
Thank you.
Yeah. Any other questions?
What about the S? What is the
Schoenfinkel. S stands for Schoenfinkel. Curry didn't know about it at first until he found Schoenfinkel's paper. He never met Schoenfinkel, but he found the paper and then he realized it was very important.
So if I were going to come at this from like a Haskell mindset, just to make sure I understand, could I think of x as a function that returns a function?
Yes, yes.
Okay.
Everything for a moment now is a function. Okay? The problem is, if I'm thinking that way, how many functions can we have? We have to be careful there. We can have lots of functions that apply to lots of functions, but we have to be careful about how many functions altogether there, and so I'll discuss that later. Other questions? Okay. And then I made a question there about the notation as I marked before. So let's see, of course the identity combinator is very trivial. So if I take the identity combinator and say, let's look at the identity combinator on some input A there, I'm going to test the identity combinator as that combinator applied to A under the benefit of the reduction rules, conversion rules as they're sometimes called, conversion there. So now I'm going to run the conversion rules once, and of course the identity rewrite rule is so simple-minded, I only have to apply it once to get rid of the identity combinator. So that's really, really trivial. Okay? So you see, I defined the combinations I wanted to look at. I called up the rules, the rewrite rules I want to apply to them, and then I applied the rules once. Mathematica, you have to be a little bit careful in using Mathematica. I think it's quite a good language, but it has its own philosophy. What it does in rewrite is you have a long expression here. Should say this way. You have a long expression, and you start rewriting here, and you rewrite something. And you say, oh, goody. And now you read the rest of the same initial expression and see if you can rewrite something else here. And then you go along and rewrite over there. When you rewrite, you may create things that can be rewritten later. But don't do that the first time. Just read from left to right. We'll go back and read it again, and then we can do more things. But you just do it once the first time, but it could happen several places in the expression. So now I'll do the S combinator here and see how that works here. So I'm going to apply a combinator made up out of combinators, S of k, and I'm going to apply that combinator to an arbitrary input A. And let's see what happens when we apply the rewrite rules there. So what happens is the first time I get rid of S, as it's obviously going to be. Second time I apply it, I'm going to get rid of the k's. So I had to do the rewrite rules twice, and so SKK is the same as the identity combinator. This is awfully simple-minded here, and some people are leaving the room because it's so simple-minded, but I just wanted to show you how, based on very simple rules, you start making more and more combinations.
Could you run the code a second time, please?
Yes, I'll go back and do it a second time. I hope it doesn't. Sometimes when you do assignment statements, you confuse yourself when you try it again. So there, I made the assignment of that particular combinator that I just wrote down symbolically there. And now I'm going to test it by doing the rewrite rules once. And the first attempt eliminates the S there because the k's weren't in a position to be eliminated in the beginning. S was in a position. S of k of A only allowed for the S rule to be applied. But now, as I've done that rewrite, I can take the result and rewrite it again, and now the k disappears. Yes?
On the intermediate steps there, so we have k of A and k of A, right? And are they, so do they get composed?
There is no intermediate step because all k does is discard the second argument and use the first argument. So
No,
But k is the identity, isn't it?
no, k is the constant function.
Oh, it's a constant, okay.
Yeah,
takes two arguments.
k needs two arguments. Identity only needs one
Oh,
argument.
okay. But it gives back the identity, or it gives back the first
Well,
input,
this
not the second.
particular, yeah,
Yeah,
yeah.
okay. Yeah.
right. Question?
Just for a moment going up so that I could just write down the rules, because I assume we're going to use them all.
Yeah, sure. So we can, they're very easy to remember. There they are. Is that readable enough on the thing? Please.
Does it evaluate the unused argument when it's constant? So like if it needs that,
No,
it
it can only, in doing rewriting, you can only apply the rules that you have.
I mean just when you have your two argument values,
Yeah.
you have to rewrite one of the argument
Okay, well
values
that's, I think this is the thing that I was explaining here, so let me try it on the board again here. S, K of A, okay? Now, I read it from left to right and I say, oh goody, I can eliminate S. And what I do is that distribution to get K of A of K of A. But that first time, I didn't know that K of A was going to turn up. So that's why I have to do it a second time to eliminate the K. Yes?
Does it make sense to apply S partially only to the first two arguments with the reduce, or that doesn't make sense to reduce?
Yes, and when we talk about the model, you'll see exactly what happens there. Keep that in mind. One thing that Kleene did by means of Turing machines, curly brackets E of n is a partial function. It's the universal partial recursive function. Okay? It's partial, but when you make combinations with curly brackets E of n many, many times, then sometimes when you try to evaluate, you get a value, and sometimes it's undefined. Okay? And so those are called partial combinatory algebras. So Kleene simply took all of the stuff he did in his thesis and turned it over to the partial recursive functions and wrote all those theorems there, and he didn't have to tell anybody about lambda calculus after that. But partial combinatory algebras are very analogous to what I'm doing here are total combinatory algebras where we can take any combination at all. But it's a good point to think about evaluation. And so if you look at the way Kleene used curly brackets E of n, you can relate to that. Any other question? Okay. So SKK is the same as the identity combinator. Okay. But lo and behold, SKS is the same as the identity. And now maybe I don't have to run it here. We can imagine it. Distribute the A. K of A of blah. K eliminates the blah, leaving you with A. So SKS is the same as SKK. Okay? So many different combinations will turn out to give you the same results. And it's terribly confusing because it's a recursively unsolvable problem whether two combinations are equivalent or not. Okay? Now, let me make up other combinators. Well, after I do these combinations here, maybe we'll take a brief break. Here, we'll see how we're going here. So, let me try this combination here applied to two arguments. You see, you can start compounding things. So I'm compounding inside a k, I'm bringing in an s inside a k. In other words, k is going to keep s in reserve and will obliterate something that gets in its way. That's what the constant combinator does. So let's test this, okay? Everybody with me to test it here by these rewrite rules. So the first time I do it, I take those extra arguments, x and y, and only the x got distributed there. Okay? But now the k can do its dirty work to bring s into play, and so when we do it again, the k puts the s in the front. And now the s can be eliminated, and oh, there's still a k there. I have to do it once more, and now after I eliminated all the s's and k's, I magically was able to define composition of two functions in terms of s and k. All combinators can be gotten just from s and k alone. So composition of two functions is the combinator s of k of s of k. It's not too hard, this one, but if you look at Curry's book, he has horrible combinations in his book. And he could think in terms of them, but it takes a special mind to think in terms of those combinators. That's why they're more beloved by machines than by people. Let's see what my other question was here. Oh, it's the move to the next one. Should I go on here a little bit more before we take a break?
Scroll back up.
Question?
Scroll back up.
Oh, scroll back up. Sorry about that.
So he found that you could create all the other combinators with S and K.
Yeah, I haven't proved that yet. I'll prove it in the next section here.
Okay. And then did other people find other things that you could use instead of S and K? Or is S and
Yes,
K
there are.
somehow special?
There's a lot of discussion in Curry's book about what the primitive generators are. And so there are many different ways of doing it.
Okay.
So it's can get pretty elaborate, but it's been studied. Other question?
This book,
Of what?
which is Curry's book?
Curry and Phase. It's in 2 volumes there. But go to Hindley's history there that I'm leaving out there. It has all the references in there. And other question in the back there.
You made the statement that you can use S and K to get to any combinator.
I'm going to show in a minute here.
Okay.
I'll show you why.
A question about that statement first.
Yeah, say.
When you're saying that, like, I have a combinator and I'm trying to get to it via SMK somehow, what is that combinator defined as before you have that? Is it kind of
Save your question until we look at the algorithm for doing it. Other question? So let's go and do that. Okay. So the question, how do we find these other combinators? We do it by variable elimination. Okay? So what we have to do is to program how to get rid of. See, what is a combination? I mean, the pure combinations is just a whole bunch of variables repeated in any order with a whole bunch of square brackets, as long as you're making it coherent there, that an opening bracket has to be matched with a closing bracket, right? So a combination, a pure combination, is just a whole bunch of variables put together with square brackets, okay? So maybe I go back to the rules here. You see, the original combinators said if I look at a combination like x, or if I look at a combination by x of z of y of z, or if I look at a combination that's supposed to have two variables in it, but it's actually just x, those can be achieved by our given combinators, okay? So a few combinations can be replaced by a master combinator there. That's our choice setup. But what about other combinations? That's the question. What about other combinations? Okay? So now I have to set up an algorithm, and this is not in lambda-calculus, this is in Mathematica's Mathematica symbol manipulation language there. It says, let's change to combinator a combination with respect to certain variables. Okay? And so what we're going to have to do is to remove the variables one at a time from the list of variables there until we get a combination of s's and k's that does the right thing. Is the question clear? Okay, so Mathematica can let us do that symbol manipulation there. So if I have just a single variable and I want to remove that variable with respect to itself, that's just the identity combinator. If I want to remove a variable from a combination f of the variable where the variable doesn't occur in f, it's a very popular law that says if you remove the variable v from f of v, oh, that's just the function f. So I'm going to use that as part of the algorithm. I'll discuss whether that's always you want to do it a later time there, but it's a tidy thing to do, okay? Now, if you have a combination h where the variable v does not occur in it at all, removing the variable is to call the k combinator. And you can do that for any combination h by means of k of h there.